Welcome to my talk. I hope everybody got lunch today. First talk after lunchtime on the microservice track is about anti-fragile cloud architectures. So now you might ask yourself, what is anti-fragile? I think 2 years ago I would have written robust cloud architectures, but I read a book about anti-fragility, which is not related to software, by the way, and that brought me in the last months or years to think about how to build anti-fragile cloud architectures. Topic today will be about cloud. It will be about microservices. My relation to microservices is that I've built a few ones and I failed with them as well. So a few ones were successful, a few ones not so successful. So the goal of this talk is to show what basically in a combination of cloud microservices problems you get and what are strategies to solve them, those problems that you introduce into your application. I'm not opinionating about if you should use microservices or not. I'm going to show why this is a valid approach, and you should make your decision on yourself. So why is cloud there? Cloud is there because I'm not talking about the classical server computing thing like you have a big mainframe or a big server and nothing changes. I'm talking about architectures that can evolve with the infrastructure. And this is what I understand under cloud computing. So with cloud computing, I really understand you have almost cheap hardware, so you can just afford to add new hardware into your cluster. You can scale up hardware pretty fast, and you can also scale them down. So that's my definition of cloud computing for now. I've built a few applications on the Amazon cloud, for instance. And the nice thing on cloud computing is that it's getting cheaper each and every day. So Amazon or Google or Microsoft, they are not giving us money by cheaper prices because they are a nice company. They just give us money because the hardware cost goes down approximately 30% a year. So this is the economy of cloud in the first sense. So hardware is just getting cheaper and cheaper because the big players, they make a pressure on the vendors. The vendors produce more cheaper hardware. And in one way, they move the failover and all this stuff to the software. So Amazon is a good example, is a cloud infrastructure that says, well, your server, it might just fail, the network might fail, the services might fail, your software must handle that. So it's the other side compared to server computing, where you buy the big boxes and they will, at least they promise, they will not fail. So, but this cloud computing gives us options, and this is why we come to microservices as a viable approach. The CTO of PayPal has created a scale cube. So this is like a 3D model. And he says you can scale your application on 3 axes. So there are 3 ways actually to scale your application. The first way is that you can do with the monolith as well, is to duplicate. We know it from the past. If you had 3 servers, they could not cover up the users. You just add a 4th one and you probably can handle the load. So the second axis of scale you could use was partitioning, also possible with monoliths. So if you had one server for the US, for US customers, you create one for Europe, for the European customers, separated data centers, separated databases. The new axis which is coming into the play here is to modularize the applications. So it means basically splitting the app in small pieces so that you can scale individual pieces of your app. And this is basically how you can combine those 3. So let's say you have a simple application. Probably you started getting users and more users. The typical way, regardless of your application architecture, is to just duplicate things. So you had one server here. You go to 2, you have a load balancer, you duplicate the database with a read replica, which is a concept MySQL and Postgres know. And then, yeah, that's it. You can just replicate the server. The problem is you have to replicate every time the whole functionality. Even though just 10% of your functionality is a performance bottleneck, you have to replicate the whole engine. So the second step is basically, yeah, to get into modularization. That means splitting your application into very small pieces so that you can individually scale up and scale down the things. If you look at typical performance problems with application, it's 10 or 20% of your code base produces almost 80 to 90% of your performance problems. So quite often you just need some pieces of the application to be basically scaled up, and most of the other ones can just be like they are. Yeah, the third one is partitioning. So using multiple data centers. So now basically what means cloud computing? The one thing is you can scale, and you can scale with smaller steps. So this white line here, as we see, is a typical server environment. So you have the load is increasing, then somehow people understand the servers are not enough. At some point of time, you add a big server, and then the server stays. With cloud computing, the idea is that you can scale up, but you can also scale down. And this is quite a challenge, because you have to work stateless. Your application must be prepared that it can handle failures. And in the second part of my talk right now, I want to discuss techniques, how you can create those architectures that can actually also scale down and not just scale up the whole time. So one technique is, yeah, you name it, service. So people call it microservice. It's quite interesting. The bigger company like Netflix or Amazon, they don't call it microservice. They just say we have a service-oriented architecture, not a microservice-oriented architecture. So they do not reason about a size. They just say every feature that we expose to clients is a service in our case. And those services, the size of the service, there's a pretty good book to read, in my opinion. It's Domain-Driven Design. And you should read the book, if you haven't read it, from back to forth and not the other way around, because it starts with how to separate your app, how to separate domains. And one way how you could size microservices, because it doesn't make sense to have a database service and a middle tier service and a UI service, is with bounded context, so that basically you start and slice your domain. And then basically it starts to make sense to create modules. So I created a microservice architecture, which I did not fail. This was a successful one. This is basically a therapy module for healthcare industry. And basically there you should start and think from a domain perspective how to separate things, but also how to collocate things, not to create microservices. This is also crucially important. If somebody just goes there and creates for each database table a microservice, he will likely fail. If somebody just creates for a big SOAP web service for every method of that SOAP web service, a microservice, he will also probably fail. So separating the domain into separate parts is not an easy process. It's basically domain modeling that you have to do, taking domain-driven design aspects into account. And also you have to figure out these services, when it comes to stability, is basically how they relate to each other. So there is a definition on domain-driven design, how the services relate. Are they in a partnership? So basically both services evolve together. So interface changes can happen on both modules because they work on a partnership. So both sides are in my control. Or are those services a conformist? So that means this product service, this dosing service conforms to that interface. So this one on top is not able or will not influence this service. This service will have an own life cycle, will have interface changes on its own. Or do you basically have a shared kernel? So it doesn't make sense every time to split everything in microservices. If you understand that, you have a functionality which should go together, I would just bring them together and not create a service just for the sake of having a service. So if you do that, and if you have a big application, you end up with something like this. And it's harder because you end up with something like this, because microservices are hard. The biggest problem on microservices is that, like the CTO of Amazon says, everything fails all the time. When you have a monolithic application, there are two likelihoods that could fail. One thing is the application server cannot connect to the database, or somebody from outside cannot connect to your application server. If you have 8 services, you have the whole problem more than 8 times, because the services cannot probably connect to each other. And this is one important thing. When slicing microservices, please never forget network. If you look at these statements, I will explain where they are from. The network is reliable. Who thinks this is true? Nobody. Okay. Latency is 0. Hopefully also nobody thinks it's true. So you see there are a lot of statements with bandwidth is infinite. Network is secure. No, it isn't. Topology doesn't change. It changes each and every day. There is one administrator. No, it is not. The transport cost is 0. It's also not true. And the network is homogeneous. This thing is not something from a new shiny microservices book. It's already published 1994 from the people of Java, from Sun Microsystems, from engineers, from fellows. So as you see, it's very important that even though modularization can bring you benefit, you should think about the foundation of it, networks. The first thing that you should start towards an anti-fragile architecture is think carefully about timeouts. One example I had in my past experiences is, for instance, simple things like getting messages from JMS. So this is a JMS API, actually. There's a receive method. If you don't work with timeouts, you're probably stuck in that method forever, because at least on WebSphere MQ, I figured that out, is you might be stuck forever if some firewall or somebody in between closes the connection and your library does not recognize that. So every time use timeouts, simple as that, on a receive. Biggest source of timeouts is also the HTTP receiver. If you open a new URL and your JVM has by default an infinite timeout, you might be stuck the whole time. And I will show techniques like Hystrix, how you can solve the problem to not kill your application servers. But anyways, you should carefully take care when you communicate with others that you have very short and aggressive timeouts so that the threads are not stuck. The same issue which I face quite a lot is waiting on your data source pool. So the more database connections you have, the more people fight with. By default, there are a lot of pools out there that have an infinite wait. So if somebody consumes your whole pool, your whole threads will be just stuck because they will not get a connection to that. So this is the first lesson on timeouts. And as a consequence on that, think very carefully if you communicate over the network to have timeouts each and every time in place. Almost every API delivers some sort of timeout either during the operations or during the configuration phase. Other than that, there are different other patterns. And there is a very good book on the market. It's called Release It. The title is awful, because for me, when I read the title, I thought it's about Maven and continuous delivery, deployment, and all this stuff. But this book is, in short, about how to write software that your phone or pager does not ring at 3 o'clock in the night, because there are some incidents. So how to write software and run the software in production. And there are companies who basically drive that, and one of them is Netflix, actually. They are just important because they have so much traffic and they open source their stuff. And the other one is obviously the Spring.io portfolio. There is a framework called Spring Cloud, which we have seen today in the morning. Who was in this session today in the morning, so that I get an understanding? Almost 60%. With Spring Cloud, basically there are pattern implementations. Spring Cloud is a project which is twofold. First, it supports cloud infrastructures, Amazon, Cloud Foundry, and others. And on the second one, it implements patterns that you can use in your application, even if you're not doing cloud computing, but microservices deployment. So don't be afraid of the name. There is no better one, I think. So cloud means here basically everything which is dynamic, but it does not mean that the environment must be dynamic. Spring Cloud is heavily relied on Spring Boot. So the idea is that every unit that you have is as simple as you have a Spring Boot application, you have, for instance, a data source configured, you have a servlet container, you have a management library called Actuator. The only thing that you need is a Java runtime environment, and you can run that application. And the nice thing on Spring Cloud is it helps me to write microservices, but it helps me also to run, I call it infrastructure services, which I'm going to explain now. So with Spring Cloud, in the end, you can really build a flat microservice architecture where you have your services, your business services, but where you can also run the infrastructure services like a service registry or so on. So the first pattern is, today in the morning we have seen Hystrix, but I want to discuss it more from a architectural perspective and also what implication that brings, a circuit breaker is, like the name implies, a circuit I can introduce at several points in my application. I should not overuse it. I will explain it later because it also imposes some performance penalties. But the general idea is of a circuit breaker that I can execute timed commands. So whenever I execute something which could time out, so because the server which I call is not available or whatever, I just execute it as a command, and that command is timed. Because the idea is, if the command does not return quite in time, it will just be cancelled, so that the server gets not stuck, because all the threads are waiting. The commands can have fallbacks. So if you have multiple servers, you could try one and then the other one. Or you could have a sensible default implementation. So this is an example, a classical thing that I've seen as you can basically, if you have a search engine externally and it's for some reason it's not available, here, this search method, you can then basically specify a fallback here, and then the fallback method is called, which gives an empty search result. You could show the user a warning, I'm sorry, the search does not work. Nice thing here is on Spring Cloud, you have one annotation you have to put in your already existing Spring Boot application, which is called Add Spring Cloud Application, which is quite new. It combines a few other meta annotations of Spring Cloud, and then you're good to go. So these circuit breakers can be monitored, as you've seen in the morning, so you can see how many went through, how many are errors, if the circuit is open or not. And in the end, you can create really a big dashboard which you can use. So this is running a command. But what does Hystrix as well? The question is, if Hystrix runs a timed thread, basically then it must execute it in a way that it can cancel it. And that is the called second pattern. It's the bulkhead. So let's imagine we have a Tomcat thread pool, which, depending on the configuration, has a certain size, and the requests are coming in. So you can run the requests, you can execute them, and servers are pretty good to execute them, actually. But if you have a service here, which is malicious because it does not have a timeout, so it just waits and waits and waits for some reason, wrong database pool configuration or whatever, then all your threads at some point of time will be eaten because you have one global thread pool of your application server, or servlet container to be more specific. And the idea of the bulkhead, and that's why Hystrix supports that as well, is that you have a separate thread pool for each of your classes that uses a circuit breaker. So basically, you hand over into a separate thread pool. That basically means if one service hangs, then no dispatches are made anymore because the thread pool will be full, and then it will immediately go back. So in the worst case, if a thread pool of one circuit has 20, you have at most 20 threads waiting in the timeout, and not all your threads queuing up at the time. This is nice. It brings advantages. It brings stability. Here's, for instance, a log file where you can see if you are outside the command, you see the thread name is something like HTTP neo auto1 exec, so it's very likely a Tomcat thread. If you are inside the command and you print the thread name, you see here you have Hystrix, which implies it's a Hystrix managed thread. REST currency exchange, that is the class name, and then the number of the thread. So you see you are here inside. This is nice, but this gives you a few issues. First one is thread locals. So if you are running your application, you should do the Hystrix circuit breakers at a level, probably at the service level. So then it plays nice, because inside the service level, you're also doing security, typically transactions, and all the thread-bound things. If not, you can work around. There are ways to instantiate Hystrix variables and to work with that. The third way is you use a semaphore barrier instead of own threads. That saves you switching costs, but that comes at a cost that you do not have separate thread pools. So the point I want to make is, even though Hystrix seems very simple, you have to think about How often do you use hystrix? So where do you basically create the circuit breakers? In my opinion, it's not a good idea if you have a service call through 4 methods to create 4 circuits with own threads, because it just imposes a very high switching cost to the application. And you should think if 1 circuit is enough in your application, typically at the service level. Next thing is service registry. If services want to talk to each other, you need some kind of registry so that you can replace services. We had that in the domain that I've shown before. We had that services are even dependent on the user profile. So if the user is a US-based user, he typically uses US-based services, but if he has some special settings in the profiles, he calls some special services. So with the service registry, you really decouple them. Spring Cloud, as an implementation, supports all the 3. Console and Zookeeper are pretty new, so they are currently in a milestone phase. The Eureka from Netflix is very mature in the sense it's since the first release available in Spring Cloud. Console and Zookeeper are newer ones. Those service registries, they have basically differences in consistency and availability. So Eureka is very much designed to be available. It's run by Netflix in a multi-region setup, so it's run in US and Europe. So if even if a data center fails, it will run. Console and Zookeeper are more about consistency, so they are not designed that much on availability from the CAP theory. The biggest difference between all the 3 is the lookup, because each service registry has a different way how to discover services, and this is what I'm going to show, because that might basically influence the kind of service registry you want to take. And this is called the discovery, the client discovery. So if you want to call a service, you first need to do a service registry lookup. So one technique that is possible is to have a local DNS server. So in some way you make a normal request, and then there is something, for instance, in local agent, in the case of console, or on Kubernetes as well. So if you have Kubernetes or console, you basically call the services, but you have a virtual DNS name. And your local DNS server on the machine will resolve then that service. So that is probably DNS-based lookup. So then you get the service. It's important that you have a DNS timeout of 0 so that the information is very accurate. And then you can basically call the service instance. This is how console Kubernetes works, for example. So console installs a local agent, and this local agent basically allows you then to do a DNS lookup on the machine. Kubernetes manages the DNS names on your machine if you run there. The other way is how Eureka is doing that by having a separate discovery library. So you have a Java library which runs in your execution environment. Execution environment here means the JVM, not necessarily the machine or container. So you have a discovery client, which is a Eureka client, and then you get the services, and then you can load balance to your service instance. It has advantages, also disadvantages. The advantage is obviously, if you're a Java developer, it's very easy to discover the things. You do not have to think about DNS timeouts. You do not have to install an agent, like for console, where your setup is more complicated, even though the application lookup is easier. So talking about a microservice, the Eureka way is more versatile because your Spring Boot app is still fully self-contained. If you have a console, you need to install something on the client machine. So the discovery client will get the services from the service registry, and then you can dispatch them. There are also other ways to work. If you are not on the Java world, you could use a sidecar technique, which is called Prana. So you can basically, send a proxy request, a generated one, to Prana, and then he looks up the service and then load balances that. This is especially important. Let's say 80% of the application are running on Java using Eureka client, and you have a few clients which are probably not on Java, so then you can use Prana, which is their sidecar implementation. The other way is you use just Zool. So Zool Edge Gateway, everybody can make requests. This can be a JavaScript or something, and based on the content, on the URL rules, basically the service is looked up and the service is dispatched. So you have to think carefully what techniques or what way you want to do. Spring Boot, like I said, supports all the ones. Also, Prana can be bootstrapped in Spring Boot as a sidecar implementation. So it's up to you. Load balancing. I just showed that load balancing is possible, but it's also something you have to take care of. Where do you load balance? The simple strategy is, if you use Ribbon, it's a round robin. So it takes some service. Availability filtering, so services which are disabled are not queried at all. And the other one is the weighted response time. This is especially useful if some services starts to backfill, if they start to get slow and they do not respond in time. So then basically with the weighted response time you will get the fastest service at all. You can also do zone affinity, so you try to call a service inside your data center, then inside your region. If that does not work, then even outside. So there are different strategies you can plug in here. Ribbon is supported on Spring Cloud pretty nice because it's an HTTP interceptor in the REST template. So whenever you do a call with the REST template, the HTTP request is intercepted. The logical name that you give, so you give HTTP/service name, is then translated to the physical address, and then the HTTP request is processed. So in the best case, you do not feel or see anything in the REST template about the load balancing itself. Obviously, there's also the possibility to do server-side load balancing. So you could do load balancing through a load balancer implementation like Elastic Load Balancer. The client-side load balancer gives you the possibility to define those strategies in a very, let's say, without an outage. So your application could even switch strategies during runtime, which is not so easy with a hardware load balancer because resetting the configuration of a load balancer is not an easy job. So the last bigger thing you should think of, it was one application I went to the customer on site and they said, well, we have built a microservice app, but the application is too slow. That's a problem of your chatty API. If you do especially hate OAS or HAL, and everything is then fetched later, you work with references, and your client does it, it starts to get slow. Because the problem is you request too many fine-grained resources. Because the general idea is nice, that you hyperlink resources to each other, you do not have any duplication, but this is not good in the sense if you have a client here, and he is then basically resolving those references, and that makes way too many requests. Even if the requests are in some way tried to be cached. So a solution is to have an API gateway. So that basically means you have a server-side component which is physically nearby the clients, and those server-side component basically traverses all the links, resolves them, and creates you a big JSON file which contains almost all the data. There are different solutions there. You can build an API gateway almost on yourself by doing generically resolving the references with libraries like Traversen. There are also new techniques out from Netflix. It's called Falcor. That basically is something where you can work with JSON path. So you can navigate on the client side, and he will basically do batched reloads. So you need a server-side component, a proxy, which is provided by the framework, and the client side. And then basically it tries to optimize the traffic between them by doing batch requests. But this is something where you will seriously run into problems with your network if you expose too many fine-grained resources which are queried all the time. You need to think about something like an API gateway here. So this is about what are techniques. But what is the problem running distributed architectures, especially on the cloud? So even in a server environment, developing them, you have seen a few tools where you can solve problems which are commonly used in a microservice way architecture, but running them is hard. In the normal way how you run applications is you develop them and then you load test them, you anticipate how many users you will likely have. You do some kind of performance testing if every use case is fast enough, and probably some very small stress testing. Well, let's kill a server here and let's see what happens. And this process is called hardening. So you try to imagine what can happen with my application, and you try to create a robust architecture. A robust architecture is nice, so it's better than a fragile one, because a fragile means you did not do any load test, performance test, stress test. But it's not so nice because failure happens still. So a good example is Amazon, if you run on them. They sometimes create failures. And almost all the failures I can imagine in my short history with Amazon is almost every time network traffic. So the first incident that happens is network. Even there's some load balancer. This was one of the biggest failures at Christmas Eve on Amazon. The load balancers did not work, and then basically, they promise to be more stable and everything. With this failure, almost every application failed. So Netflix was down, all the bigger ones were down. And there is a theory about that. It's the black swan theory. So there are every time things happening in life which you do not imagine. This is about a Dutch explorer. He's called Willem de Vlamingh. And the people, until 1697, they thought there are only white swamps, no black swamps. And this discoverer went to Australia and discovered the black ones. So people then had to change their whole mindset on biology and everything, because there are now black swans here. And this is basically created or invented by one guy who wrote the book Anti-Fragility, that basically means it's something additionally on resilience and robustness, because the anti-fragile system gets better when there is a failure happening. And that's the overall idea, to create anti-fragile architectures. Second failure, so Netflix learned from that failure, and now the second failure happened last year in October 2015. There, basically, the Amazon service, the DynamoDB service, which is very important, failed again, network disruption. So it's every time the network. But at this time, nobody or very less failures were suffered, because Netflix has trained that. So they really trained their architecture, or designed the architecture, that they rerouted the whole traffic into another region. So even though the whole region failed, they just rerouted it because they embraced the situation. They know this happened to us 3 years ago, and this will happen. So what are techniques? You could start very simple. You could create, or you could harden your application. There are Linux tools, just as an example here. There is a tool called Netem, where you can basically influence your network. So you can add latency and just see what happens with your application. So just delay the packages for a few times, and then see if your application still runs. You can corrupt packages, so just corrupt 5% and see if your application still works. You can drop packages, so drop a few ones, or you can just block the DNS. And that's the general idea what you should do in the best case, even in production. This is what an anti-fragile architecture means. In the semi-best case, you do it in your test environment, because just with this, things like this, you just train your architecture or see how it behaves. Otherwise, you will see it when it really happens, and you can't do anything. Same thing is for I/O. You can just write your disk full of bytes and see if your application still runs. You can just burn CPU as you want and see if your application still runs. So this is something what is called failure injected testing. So at a minimum dose, a very small dose, 1 or 2% of the application, you include such events here and there, even in production. And if you have histories, if you have service registry, if you have dynamic discovery and all those sort of things, then your application should just keep up. Because if you have 3 services and one service has serious network problems, Historix should see it, Ribbon should mark the server as not usable and just route to the other ones. So that is something where there's also software available, so you do not have to go into your Linux. It's called the Simian Army. It's a failure testing or failure injected testing library. There are different libraries out there, so it's a latency monkey, which basically does the delay of the network. There is a janitor monkey, which cleans up stale servers. And there is a chaos gorilla, what they call, which really kills the whole data center. So yeah, from the perspective of the application. So this is also something you have to train. If you want to do a failover to another region, you have to train it before. Otherwise, it will just not work. And this is why it worked last year, because they train it each and every day. And this is something that happens to you. For instance, AWS reboot. This happened also last year because of a security issue on the Xen hypervisor. They had to restart around 10% of all their servers, so the whole Amazon cloud. It also affected us. For Netflix, they had 2,700 Cassandra nodes, more than that in production. 218 have to be rebooted. 22 even did not come back. So the JVM did, or the virtual machine did not start. They did not have an outage here because periodically they kill Cassandra instances to just make sure that the system is healthy and alive. So coming to the conclusion about anti-fragile architectures, it's something that happened to me as well. We brought a big application live in the past, and every error we had was hardware related. And in an anti-fragile organization, people say every engineer is an operator. So it's very easy to say, well, that was hardware, it's not important for me, but you should every time see what was the cause and how can we avoid that. This is the general idea of an anti-fragile organization. So not just seeing the problem, but also understanding how this could happen and how you can basically avoid the black swan here. All right, so I think we have 3 minutes left for questions. Are there any questions so far? Who is doing microservices with the Netflix stack here? No hands up, okay. Who plans to do them? Okay, only 10. Any questions on microservices, Spring Cloud you might have? Yep.
Do you have any experience with splitting up a database, maybe a database into several parts and running the microservices?
Yeah, the question is if we have experience or splitting the database, yeah. I think it's very important that you have a separated data model per microservice or bounded context. In my opinion, they could run eventually in the same database, probably with another user or schema space. So separated, I do not think you need an own physical database for each service. But if you need to join data between two microservices to retrieve them, it's very likely that the decoupling is wrong, the abstraction. So for me, it would be a flavor that I should rethink if the separation makes sense or not. This typically happens if you have a relationship which is both sides directed. If it's one side directed, it's rather easy because then you have to say who is the owner of the relation, and in REST you also have hyperlinking. It starts to get interesting if you have a bidirectional relationship, but then I would start to think if it really makes sense to create two separate microservices, because in some way you have a tangle anyways, because both are tangled, which is not meant to be bad in domain modeling, but then it would be, for me, it would be hard if you start to create two separate microservices, because you are assuming they are separate, but the data model or the domain model assumes they are together. So I would try, and this is something which is a good practice anyway, to challenge why do I have to access the data from both sides? So why it's a bidirectional relation and not a single directional relation. Okay. Any other question? Yeah. Yeah, I mean, the general idea is why there is a concept, each service should have its own data model, that you can update the service And in the best case, the service has a backwards compatible API. So even if you have a service registry, you can run basically the old ones. Then the question is, how do you switch? So there could be a cold switch, a very short outage, where you basically migrate the data model. Or if you can do the migration because it's also backwards compatible, so you only add a few new fields, but do not change the structure, you could do it even live. So you bring, as long as the interface is stable, you bring in a few new services, they register themselves in Eureka or some other service registry, and then gradually you start to shut down those. So you can also do some kind of canary, so you install 1 or 2 new versions, see if they work, how they behave, and then basically you shut down the old ones.
Can you tell Eureka to not use the old ones anymore?
Well, Eureka by default is very proactive to you just deregister and then almost instantly it's not used anymore. Yeah, so they're very short. I think it will take you up to, it's the time of Eureka and the time of Ribbon. It should be 2 or 3 minutes in total, so it's not a long running thing. Yeah. Yeah.
Obviously, Spring Boot is quite well integrated with Registry, so would it be possible to integrate other technologies like Node.js or .NET-based microservices with Registry? Do you have any experience with that?
Yeah, first of all, Hystrix is really a Java implementation, so I'm not so familiar in cross-language things. I mean, you could run JavaScript on the JVM, but it's a Java thing. There is a Java Nika implementation, which is aspect-based. So you could, in theory, in each Java environment use Hystrix. There is load time weaving, there's runtime weaving or compile time weaving available. With Spring, it's nice. You do not need to change anything because the proxies are built at runtime. Outside Java, I have to confess, I don't know. Probably there are circuit breaker implementations out there for the languages, but Hystrix is really a Java-only implementation. It is really mature. We use it also in a high concurrency environment for a national bank that clears all the trades of the whole day, and we never had problems. The biggest issue is to tune Hystrix. You have to understand what means this new threads, and do I need that, and what is cascading, stuff like that. So, but once it runs, it's pretty mature, and it is also, it is visible, because if exceptions are thrown, you get a Hystrix exception. So if you catch exceptions, you have to think about, well, there is some circuit breaker. You can obviously extract your exceptions so that you shield Hystrix, but it's still intrusive in a way. I mean, it changes your threading model, it changes your exception propagation, so it's not something like, hey, cool, I have a library, let's annotate that and it will work somehow. It's not the case. Yeah. But it's stable. So once it's the things about thread state and everything is properly configured, then it's stable, in my opinion. Yeah. All right. So the next speaker is coming, so thank you for listening. And I'm here for the next hour if you have any questions other than that. Thank you.